Welcome to the 30th and the last lecture video for Physics 4B. We wrap up this semester covering electromagnetism and circuits. A separate wrap-up for thermodynamics was done in lecture 6. In the first half of this lecture video, we do a short topics review of electromagnetism and circuits. Continuing from the last time, a similar review was done for electrostatics and magnetostatics. And we demonstrate the use of a computer algebra system, that is CAS or CAS, for solving time-dependent circuits. In the second half of this lecture video, we work through some exam-type questions relating to electromagnetism and circuits, titled Electromagnetic Induction, LRC Circuits, and LR circuit. Thank you so much for following our course content for the semester over the 30 lecture sets, adding up to more than 55 hours. I hope you will look at our course content for Physics 4C, covering optics and modern physics. The topics that I set aside as electromagnetism, and that is actually the proper way to refer to the theory that you have been learning this semester, because you saw on Monday that that in Maxwell's equations that electricity and magnetism is blended into one coherent theory where you cannot describe electric fields properly without magnetic fields, and you cannot describe magnetic fields properly without electric fields. So the very first topic in what I'm calling electromagnetism would be Faraday's law. The expression of Faraday's law actually says it all. It says that there's this new kind of electric field that we hadn't seen before. New kind of electric field where if you integrate around a loop, you don't get zero, you get a non-zero quantity. There's an induced voltage as you go around in a loop. And this induced voltage is related to magnetic field or change of magnetic flux. So this was our introduction to electromagnetism. How you get something that's electric directly from something that's magnetic. So we have Faraday's law, and I guess that's probably it. So this is not going to be a big part of your exam, but so Maxwell's equations would fall under here. And you know, as a physicist, my dream would be that everyone would know what Maxwell's equation is, feel comfortable with what it is, and would have it printed on their T-shirt, which some people do. But you know, we only get introduced to the entirety of Maxwell's equation only towards the very end, because Faraday's law is the very last full equation we give to you. And actually, we waited until last Monday to introduce the last piece of Maxwell's equation. So you know, I can't really focus a lot on Maxwell's equations, so I won't. One thing I can tell you is that I'm going to ask you to know that last piece we introduced on Monday. And if you want to look it up again, and I'll eventually post a video, is the key phrase that you want to know is displacement current. I mean, there's a whole story that goes with displacement current, what it is, what role it plays. Read the textbook. But that's the key phrase. You have to know what displacement current is. And that's the one part of the chunk of stuff we covered on Monday that might be on your final exam, because this is the last piece that's needed to wrap up the complete Maxwell's equations. This is Maxwell's contribution. That's why we call all the equations that we are introducing throughout the semester, Gauss's law, Ampere's law, and Faraday's law, as Maxwell's equations. We don't call them Gauss's equations. He has enough things named after him already, if you take multivariable calculus. So this is electromagnetism. It's all fundamental physics,
like basic nature, and some limited applications, but I guess if you found a lot of this was very abstract and you are thinking, why am I learning this stuff? I'm a mechanical engineer, I'll never see this again. then that's not entirely unjustified. So what I believe is the most practical part of this class is actually circuits. I mean, even in circuits, you might still think, I'm a mechanical engineer, I'm never going to deal with the circuits. That might also be true. Or, I'm a civil engineer, I'll never deal with the circuits. This is circuit stuff, it's more useful for people who are doing research, because when you are doing research, you are going to be dealing with some type of data-taking apparatus. And most of that is electronics. So you have to, if you're a physics major, upper division physics major actually includes an electronics lab, because it's so important for a physics research scientist to know about electronics. That's basis of the data taking device. And if you're on X major, electrical engineering and computer science major, then this stuff would matter more. But I think every engineer can know something about circuits that would help you in some aspect of your job at some point. Maybe not for every engineer, but I think it's one of those things that everyone who's technically minded should know. So as far as the circuits go, we divide them into sort of three big areas. That those three big areas would have slightly different approaches to it, but there's some still common threads through it. So let me just name those three big areas. They would be DC circuits, time-dependent circuits, and AC circuits. Those are the three big sort of breakdowns of problems or situations that we would call circuits. DC circuits is what you saw in exam 2, along with electrostatics. So DC circuits that's where we introduced, for example, the Ohm's law here. And time-dependent and AC circuits were what you saw in exam 3. And this is where you get slight bit more complication. So both in starting with the time-dependent circuit, you had to deal with a relationship between voltage and current that were inherently time-dependent. In Ohm's law, they are not inherently time-dependent. Voltage is proportional to current. So if voltage is constant, then current will be constant. That's what DC circuit is, direct current circuit. But in the time-dependent circuit, we introduced two more circuit components. We introduced the circuit components, capacitors, and inductors. And the relationship between voltage and current for capacitors and inductors work out in such a way that they always have to be time-dependent. It involves a derivative somewhere. It involves an integral somewhere. So now, I don't want to, so there's a reason I'm putting circuits as its own category, just all in one. It's because they all share one common thread. It's that when you are analyzing circuit, you have one common standard approach you can use in analyzing any circuit. It doesn't matter if it's DC or if it's time-dependent or AC. So if you're analyzing a circuit from scratch, your starting point for any of those would be Kirchhoff's rules. And we spent a lot more time with these rules when we were doing DC circuit, with the loop rule and the junction rule. And this is the standard strategy for circuits. When you see a circuit that you have never seen before, and you need to analyze it from scratch, you do it by application of Kirchhoff's rules. So for exam 3, we didn't emphasize it all that much. You kind of have to know the loop rule to set up the differential equation that comes out of the capacitor and inductor circuit. But now that we are doing final, we might go back to DC circuit. You might want to brush up on application of Kirchhoff's rules, especially as it relates to junction rule. And those system of 2 or 3, maybe even up to 5 equations that you need to be able to set up and maybe solve. I do realize your final is only 2 hours long, so when the question is written, it'll have that understanding in mind. I'm not going to expect you to set up a linear system of equations of 7 equations and solve it in the time you have. But I might actually expect you to be able to set it up. Setting it up actually doesn't take all that much time. When you have a system of 7 equations, you can actually set it up with a careful application of Kirchhoff's rules. It's the solving portion that'll take way too long for you to actually do it in 2 hours. So you should know application of Kirchhoff's rules. AC circuit, it could have gone with a time-dependent circuit. But the reason I want to separate time-dependent circuit from AC circuit is because your approach to solving it is different. With a time-dependent circuit, it's a very straightforward, step-by-step way of solving it. As in, you set up your Kirchhoff's loop rule equation that has first-order derivatives or things like that in it, and you can actually solve it using the standard method you learned in calculus. You use the separation of variables, and you go through it step by step. Everyone here should know how to use separation of variable to solve an RC circuit or LR circuit. So that's how you approach time-dependent circuit. AC circuit, it's a little bit different. It's you could be talking about, so when I say AC, you could be talking about a driven AC circuit, or you could be talking about just an LC circuit, inductor capacitor circuit. So a driven circuit is AC because you are applying a voltage at an oscillating voltage. So you are forcing it to oscillate. All right, it oscillates. LC circuit would be where you have an oscillator in your circuit. So if you charge it up and you just let it go, then it sort of oscillates on its own. In both of these cases, you had to guess a solution. At our current level of mathematical sophistication, none of us, actually including me because it's been a while since I've done it, none of us had the tools to solve this directly. We instead guessed the solution. We guessed the sinusoidal answer, plug it in, get an answer. That's how we got the net oscillation frequency for LC circuit. So it's a different solution approach. You should know how to use it. Now, and when it comes to driven AC circuit, one particular mathematical tool that I introduced will help. This is where you might want to review complex impedances. I don't know how much of that I would have put on the final exam. I already put fair amount on your exam 3, which a lot of you got. Because it's the same question I gave you twice. But, so I guess what I would say is that do review complex impedance. I don't want to put on as much importance on complex impedance as I put on Gauss's law and Ampere's law. As in, my standard is that everyone going through this class should know Gauss's law and Ampere's law. If half of you didn't learn anything about complex impedance, I'm okay with it. Complex impedance is something that people properly learn when you are dealing with a lot of circuits, when you take an upper division circuits class for some reason. So if you don't end up learning it, then I'm actually okay with it because it's not a part of the standard curriculum for this class. But it's one of those things where it's like people call it life hack. This is the circuit or physics hack. It's where it's such a small thing. Once you understood it, that it would allow you to analyze something that's way more complicated than what you ought to be able to do at your current level of understanding. I guess here's one way to put it. If those of you who are reading through the textbook, you might have read the description of the phasors, the impedances, the reactances of inductor and capacitor, and you get the impedance and how that's represented on the phasor diagram, how they're combined in series and parallel. As you're reading through it, if you found yourself like you weren't really following it, I completely sympathize. I didn't follow it when I was looking at it. And in fact, even today, I never go back to that phasor diagram. It's this complex representation that'll make a sense of it. And the proper way to understand the phasor diagram is as a representation of the complex number in the complex plane. Like that's how. So in the text, it looks so tortured because there's one right way to say it. Say that this is complex impedance, and they're trying so hard not to say the word complex. That's why it looks so tortured and geometric. So anyway, so these are the 4 big topic areas. I would say they are probably all about equally important. So without committing to any particular distribution of questions, if 25%, 25%, 25%, 25%, that's probably ballpark distribution. As in, I'm not going to say circuit is less than 10%. No, it's about fourth as important. On the other hand, if you felt completely lost on circuit, so let's say you gave up, then if you're doing well enough on the rest, you should still be able to do reasonably well. As in, these cover 75%. So if you got 80% of that, you are at least passing. So.
Let me give it a title: Time-Dependent Circuit Analysis with a Computer Algebra System. So there are still some parts that you need to do yourself. Computer algebra system is a tool like a calculator. It can automate the mechanical aspects of the problem solving, but we still need a human intelligence for someone to take a look at the circuit, analyze it, and basically write down a set of equations that describe the system. That part so far cannot be automated, and in my opinion, it may never be possible to be automated. I mean, someone can program in some typical setups, but let's say you have a completely new circuit that no one has ever seen before, then having a guarantee that it can be analyzed, that requires a human being. That's the part of the job of an engineer that cannot be automated. So let me start out with the circuit. I guess I'll do the discharging cycle first because that's the easier one. So I'm imagining a circuit with a capacitor that's hooked up to a resistor. And for the purpose of this analysis, okay, so I have one equation in terms of one not unknown variable, but apparently an unknown function of time. And so this completes the first step. I have come up with my system of equation of one. One is still a system, and it has a right number of equations for one unknown. So yeah, so now the remainder of this problem solving step is okay, solve them. And and this is I guess in the other lecture where I do it by hand, where I spend the remaining 7 minutes. Let me do this automatically using this computer algebra system so that I can see if I can beat myself doing this by hand. So, and to, I guess, show fully the power of this system, let me not even simplify this equation even slightly. I'm just going to plug it in as it is. So I do need to prepare some things. I need to declare the variables I'll be using. So that will be Q, C, R, T. Oh, and I might use I later, so let me declare that as well. Okay. And oh, I hope I didn't override. Okay. I don't know. Let me just give this a try. Okay, I think it'll be fine. Somehow when I type in I, that's an imaginary I. This I is the current I. By the way, in electrical engineering, they define J as the imaginary number to avoid this exact problem. Okay, I have my variables defined. Let me write down my equation. So, let me just give it this a little bit of a try. So there's a function for differentiation that's called a diff. And what I want to double check and make sure is that if I don't define Q as a symbol representing a function, that I'll still be fine. So let me give this a try.
So derivative of q with respect to t. All right, so I gotta define q as a function. So let me look at the help file. How do they? Okay. Q is equal to function. I sometimes forget the syntax. Mainly because I'm not as familiar with the SageMath as my other computer algebra systems I've used for my other job for a very long time before I started teaching. I believe the place where I'll get a good documentation is the function that I intend to use to solve this differential equation. That's going to be a function called dsolve. And if you don't remember the function name, then you would Google it. SageMath to solve differential equation. Now, as I look at this solve, usually documentation gives some examples, and I'm looking to find in one of the, there it is. So that's the example. All right, let me give that a try. So Q is equal to function of Q, that's the symbol I'm using as a function of time. Okay, let me try that command derivative of Q. Okay, that seems good. So I'll go with that. So now I can write down what my equation is. My equation, I'm gonna put that into this variable. My equation is Q divided by C plus the resistance times the first order derivative of Q with respect to T. And I have to be careful with this equal sign. So this is what we call assignment symbol, because what I have in the computer programming language, because what I have on this side will get assigned to this variable equal. What I want for here is not assignment symbol, but an equality symbol. And that equality symbol in SageMath and Python is double equal sign. So that's equal to 0. So that's my equation. Good. Okay, and I guess I have my equation. Oh, so I think I'm just ready to use dsolve. Help. Well, I'm ready to use dsolve, except that I don't remember the syntax. The syntax is the differential equation, dvar. Dvar is the dependent variable, so that would be our q. Initial or boundary condition. Let me not specify them. Although I could. Let me try it once without specifying it, and then I'll specify it. I bar, that's the independent variable, so I would call that t. Okay, so dsolve differential equation that's stored in EQ. My dependent variable is q, and my initial conditions is equal to none, and independent variable is my t. Okay, let's see what it does. Oh, it might complain, I think, because these things tend to try to solve these equations under super general assumptions. Oh, no, never mind. I spoke too soon. There's the answer. So you have to be careful here. This underscore C, it stands for integration constant. It's different from this C. And yeah, that looks right. So amplitude or the magnitude is the initial charge Q naught times e to the power of the exponential of minus t divided by RC. That's what I solved. And I guess this time, this took me 20 minutes, so maybe I didn't save any time, but I talked more. And I didn't have to do any separation of variables. Let me try just one more thing, because so we have this integration constant, but one of the things is we know the initial condition, we know what our initial charge was, so it feels to me that I should be able to just get that. So if I were to write down something like q is q as a function of time is equal to c, well, constant times e to the minus t over rc. That's the equivalent of someone forgetting the integration constant, or I forgot to specify what this coefficient should be. So let me try to get a complete answer. Now, I could get this complete answer by solving for, where I said, okay, Q at time equals 0 is something, and I set that equal to be Q naught, and I can do that. But as long as I'm using computer algebra system, let me see if a computer algebra system can get me all the way there. So let me look at the this documentation again for initial conditions. How do I specify the initial conditions? So there must be some example for specifying initial conditions. Uh, it looks like some kind of an array. I don't like an array. Oh wait, initial conditions tend to. Yeah, I also don't know what that means. 137. It does nothing. Okay, I'm gonna give it a guess. Initial boundary conditions. Oh, wait. Initial conditions are then interpret. There it is. So the first value would be your initial x value. So, or initial independent variable value. So in our case, that would be at time equals 0. And then y at that value. Oh, and I guess those additional ones are for this higher order. Um, okay, I think now I understand the syntax. So the initial condition for us would be, so time equals 0. And the charge at that initial time should be Q naught, but if I do this, it'll complain because I haven't defined the Q naught yet. So let me declare Q naught as a variable that I'm going to use to indicate my initial charge. So this is our initial conditions. So let me do the dissolve again. And I'm going to say my initial conditions are equal to the variable I defined as ICS. This looks a little bit confusing for those who are not familiar with the Python syntax. What this means is, so ICS stands for the parameter keyword. This is one of the inputs to the function dissolve. So that's what this ICS stands for, parameter keyword. And with this equal sign, I'm saying, okay, set that parameter to be this value. And this value is the variable. The list that's named ICS. I think once you get used to it, it's a super natural way to write it, which is why I did it. And yeah, there it is. There's our answer. Q naught times, so, this says, oh, yeah, that is equal to Q naught. And I think I spent a lot of time just talking about how you type things in, then actually, I didn't spend any time coming up with this answer. There's our answer. We are done. Let me, so in the version of the lecture where I did this manually, it took me like 40 minutes total to do everything. Let me leverage what I have on screen here to try to do this more quickly. So far I haven't saved any time, but I can make a better argument for computer algebra system saving your time if I do the second version. So I'm going to just modify my circuit a little bit. Let's do the charging cycle analysis. So for the charging cycle, I'm gonna have to change up a few things. Then I have to say, okay, my initial charge no longer Q naught. It's gonna be initial charge will be 0. And I need some circuit element that's going to charge up things. So let me just do that here. Put up a battery here. And the battery gets inserted into this space at time equals 0. And the value of the battery would be V naught. Okay, I wonder how much of the previous equation I can keep. So let me just erase the answers that was for the discharging cycle that wouldn't apply anymore. And I think I should erase these as well. What I'm going back to is the Kirchhoff's rules. Junction rule still, gives only most trivial of the expressions. And I guess as I go across this capacitor, I can still say that my charge Q, this symbol Q here, would represent amount of charge on the capacitor. And let's say over time, we'll build it up so that it's a plus Q here and minus Q here. And then I think everything I wrote here so far is okay. And I have positive current flowing across the register, voltage drop, so far so good. Okay, and here I have to go across the battery. All right, so let me just add that additional contribution to the voltage. So plus V naught, and now I'm back to where I started. It's equal to 0. Okay, all of that seems fine. Let's think through if this sign convention that I have here is right. So I'm thinking at time equals 0. My charge starts out at 0. So charge here is going to build up, increase. So, and I want the current to be positive. Then is this right? If my charge is increasing, then minus. But that's a little bit weird because I didn't change any other part of the circuit. Why should this relationship now suddenly go from minus to plus? And I'm being a little bit disingenuous because I spotted this like a couple minutes ago. You do have to be careful with the signs here. So I was saying at time equals 0, my charge is increasing. But if you look at carefully how these charges are labeled here, the way the charges are going to build up here at time equals 0, it's not actually minus Q plus Q. Because as the current flows this way, you are going to accumulate positive charges here. So the way to fix it, you can actually do it a couple different ways. And I think the way I've done it in the other lecture is I recognize, okay, plus Q here, minus Q there, flip this sign and flip this sign. And you can definitely do it that way. That's perfectly valid. You can do that. Let me show that the other way will also give you the correct answer. You just have to be careful in how you process it. So in the other way, there's nothing for me to change here. I can retain this minus sign, and what I'll have to be careful is to recognize that at time equals 0, as positive charges build up and negative charges build up here, what I'll actually have is the Q as a function of time will be negative at small values of time greater than 0. The way you describe the charge that builds up here, you describe it as a negative charge because the way it actually builds up is opposite of how I assume the directions when I wrote down this equation. So I need that modification to the equation. And okay, so with that, let me just plug in all the things, and I end up with so Q over C, and plug it in, plus R dQ dt plus V naught is equal to 0. So that's my differential equation. The voltage of the battery should be known somehow, and then I have one unknown Q function in terms of all the other known things, so I should be able to solve it. So now let's solve it in computer algebra system. Let's see. Oh, I need to declare my variable V naught. I don't think I've used it yet. Okay, let me define my equation 2. That's going to be Q over C plus R times derivative of Q with respect to time t plus V naught is equal to 0. That's my differential equation 2. Compare and make sure it looks okay. Okay, let's solve for differential equation 2 in terms of Q. Let's start with just no initial conditions. None. My independent variable is still t, and there it is. There's your answer. And you might note that that looks a bit complicated. So let's plug in the and it has to do with this integration constant. Let's plug in the known initial conditions. So the known initial condition would be okay. I'm going to have at time equals 0, I'm going to have amount of charge equal to 0. And I think I can take a guess at what my current will be, but I don't think I need to plug that in because this is a first order. Let's give that a try. So there it is. And I think this can be simplified a little bit. So let me do a full simplify. I think that'll factor out some things. Never mind, it doesn't. Okay. What it should factor out are these C times V naught, C times V naught. They should be factored out. So let me write down the factored version of that. So the factored version of that says the amount of charge on the capacitor as a function of time is equal to, don't forget that minus sign, minus, and then factor out CV naught, CV naught times, okay, so here, let me do one more algebra step, which is, I see this here, e to the minus t over RC. I can distribute it into these two. Then with this term, you see that this cancels out that. So I'm going to say 1 minus, and this times this will give me e to the minus t over RC. Parenthesis close, and nothing else remaining there. Yeah, that's my answer. Charge on the capacitor as a function of time. And you can see here, okay, so at time equals 0, this exponential will be 1. So 1 minus 1, you get 0. As time goes on, this portion of the expression is undergoing exponential decay. So 1 minus something that goes exponential decay, it'll end up looking like an upside down exponential decay. And that's exactly what charging thing looks like. Oh, except in this particular case, because this minus sign, it'll be upside down and then flip around again because it's on the negative side. But yeah, other than the minus sign, which we were expecting, this should be the exact answer that you see me get, except 6 minutes later than what I have now. So that's the demonstration of the analysis of the RC circuit, RC time-dependent circuit with the computer algebra system. Oh, I think I said I would do the LR circuit as well, so let me do that. I think I can do that pretty quickly. So computer algebra system for a LR circuit. Let me do the version where I'm charging it up. So I have this series circuit of a battery of voltage V0 hooked up to an inductor of inductance L, finally hooked up to a resistor of resistance R. Okay, and a valid question to ask for a circuit like this would be, what is the current through the circuit as a function of time? It has to be as a function of time because of the property of inductor, which says the voltage. So okay, that's my equation, and I think I'm done because I don't have any, I don't have Q as a dynamical variable, so I just have I, and I think that's it. I is my unknown. I'm all good. So yeah, so well, I mean, it's not solved for anything, but I have computer algebra system that can just analyze the whole thing. So let me do that. I'm gonna take this here. I think I have declared all the variables. Oh, except for L. So let me declare L. And I have a feeling, wait, do I need I naught? I don't need I naught because my current at the time equals 0 is 0. So let me write down my differential equation 3 of the today. Is V naught minus L times. Oh, wait, I need to write that because when I do derivative I as a function of time, yeah, I'm gonna get this. So I need to redefine I to be a function named I of time t, so that when I take the derivative, it'll correctly take the derivative. So okay, my equation 3 is going to be V naught minus L times derivative of I with respect to t minus current I times R is equal to 0. Okay, that's my differential equation. let's solve it. Differential equation solve. Equation 3. My dependent variable I, and let's say initial condition is none for now, default, and independent variable is t. Oh, that was quick. There's my answer. So that's and this kind of looks like a charging circuit. You have some constant plus this thing. Oh, yeah, I'm gonna have to do the same thing. Put this, distribute this in so that this gets canceled out by that, and I have this exponentially decaying thing here. Yeah, I'm a little concerned that do I have two positive terms? Let me plug in my initial condition. So my initial condition for I is that, well, at time equals 0, my current I is 0. That's my initial condition. And when I say that's equal to, okay, it got resolved. So with that initial condition, the other term becomes minus V naught. Good. So there's my answer. Let me write it down. And you can see an advantage of computer algebra system. The first time I did it, it took a lot of time, practically the same amount of time it took me to do it by hand. But each time I do it, I get more used to it and I get faster. Because basically, the one thing that took a lot of time is for me to learn the syntax. And once I know the syntax, then it's a lot quicker. So my current as a function of time is equal to, I'm going to do some on-the-fly factoring and distributing. I'm going to factor out V naught because I want to. And I'm going to retain this divided by R in the factored form. So I'll have V naught divided by R, multiplying to the entire parenthetical thing. And I'm going to distribute this exponential term. So as I distribute it, cancels out this term to give me 1. Minus, I factored out V naught, so I have just e to the minus, and let me do this. It says minus r times t over L. I'm gonna write this L and R in the nested fraction form so that it says minus t divided by L over R. You can kind of go through the nested fraction algebra to see, oh, that's same as that. So yeah, this is the answer. Current is a function of time, and that looks like a charging form, as in at time equals 0, this is 1, so 1 minus 1, 0, no current. But as time goes on, the circuit charges up, and this decreases from 1 to some ever decreasing value, so you get the terminal current of V naught over R. That's exactly what you see and what you get from this equation. Let me use the remaining 5 minutes to do this LC circuit properly, because this is one where you've seen me do this circuit, but by guessing what I think is the correct answer. I did it by guess and check, and I mean, the checking portion makes it mathematically rigorous. But maybe the solution I got isn't a unique solution. Maybe you don't believe me when I say, oh, there should be 2 linearly independent solutions. So this is where computer algebra system is really useful. So let me get to this point here in the video so that I can kind of save on the writing of the equations. So I'll get to this far. So, okay, yeah. I think a little bit farther. I could deal with a system of equations, but here it's already in the form that I want to use. So let me do that. So that is the differential equation that I want to solve for. So, in the lecture where I did this by hand, I didn't have any way to actually solve for it. So I made a guess that I conveniently knew was correct. So here, now I'm going to actually do it properly. Let's see, I think I have almost all the variables defined. Yeah, so I can just say, let me just make sure derivative q with respect to t. Okay, yeah. I think, is this how you do second order? No. Wait, how do I do second order derivative? Okay, yeah, that is. Yeah, okay, that seems good. Okay, so yeah, so my equation 4, that's my LC circuit equation, is Q as a function of time divided by C plus inductance times second derivative of Q with respect to time is equal to 0. That's my equation 4. Let's try solving it. Desolve the equation 4. My independent variable is Q again. Sorry, dependent variable is Q. Let's say initial conditions none for now, and that'll give us the general solution. And my independent variable is time t. Okay. Wait, what did I? Oh, it's time t. Yeah. So it it, um um computer algebra systems tend to assume things are super general. So it's asking this question basically: is capacitance times inductance positive or negative? Of course, it's positive. Okay, but since the CS doesn't know that, let's tell it that it is positive. Assume that C times L is positive. Now let's redo it. And there it is. There's my answer. And I forget if I've done second order differential equations for this class already. Now, there's a way to do this kind of the long way. So this is your general solution. And you can obtain your particular solution by plugging in your boundary conditions. And you plug in your boundary conditions for, I think for this circuit, I had it so that at time equals 0, it was fully charged up and current was 0. And you can basically do that. You have a Q as a function of time. You can take the derivative to get an expression for current, and plug in the expressions and solve for these K2 and K1. All that's good. You can do that. Now I learned how to use it. I can use this parameter to let computer algebra system do all that for me. I can just plug in my initial condition. So as I do this solution of the differential equation, so my initial condition will be at time equals 0, and it's the condition for the charge Q. And at time equals 0, amount of charge is Q naught. And I think I already declared the symbol, so that's good. And now if you stop it here, you will have specified an incomplete set of initial conditions. I don't know what it will do if I simply do the, yeah. It's complaining because, so when you look at this, you have two coefficients that come up. And that comes from the fact that you are dealing with a second order differential equation. So there are two linearly independent solutions. And so when I stop here, just specifying what the value of the function was at time equals 0, I haven't done enough. I have to also specify what was the value of the first derivative at time equals 0. So I need to say, okay, at time equals 0, my current was 0, so the derivative of Q, it was 0. So the system actually needs that information to be able to give me an answer. And there it is. That's my answer. Q naught, that's the amplitude of oscillation, times I get this oscillatory function, cosine of t, and this 1 over square root of LC is, that's my omega, natural frequency of oscillation. So it was, in the lecture, it took me quite a few more minutes from this point on, another 35 minutes to get to that answer. there it is in the computer algebra system. And in fact, I'm a little bit over time, but I can do this as well. So when you look at the chapter 14 lecture, I actually go on to talk about RLC circuit. And this was so mathematically challenging that I really had to introduce this new mathematical device for me to be able to solve it. And all of that is true. I don't mean to mock myself for doing that. But let me show you just how easily this is done with the computer algebra system. So I'm just going to advance the lecture to the point where I have written down my system of equations. It took me 30 minutes to explain, go through this with the Kirchhoff's loop rule, and write down this system of equation. It's remarkably close to what I had before. So, with the LC circuit, really the difference between LC circuit and RLC circuit is presence of the resistor. So, when you look at equation 4, it had this, it had this, it was just missing this one. So for equation 5, let me just write it down as, I'm just going to copy these. And then just add, and order doesn't matter in adding. So add R, I hope it works out okay. R times the derivative of Q as a function of time, just the single derivative, that's equal to 0. So that's it, equation 5. Okay, I think it all looks good. Yeah. So that's my equation. Let's just solve it using this solve. Let me just skip straight to the version with these initial conditions, and I will explain why. So equation 5, this solve. Oh, yeah. All right, yeah, it's asking, okay, is it positive, negative, or 0? Well, I think if you read the textbook section that relates to this has to do with whether the damping is underdamped, critically damped, and overdamped. And I think I remember the underdamped cases where my resistance is relatively small. So I want the answer for the underdamped case. That's the one that kind of looks meaningful to me. So I think I want this quantity to be negative, because that's the scenario you would have when R is equal to 0. So let me do this. Assume that this whole expression here is negative. That's the scenario I would have when R is 0. And I just want to say, analyze it for situations where I have R that's not 0, but close to 0. So assume that, and let's just redo that. But I already assumed that C times R squared minus 4L is, oh, okay. I might have to simplify it for it a little bit. So I'll do it this way. I'm going to say this thing is less than the thing on the right. That's identical to saying that this thing is negative, but it's specified in a way that's a little bit easier for the computer algebra system to digest. All right, assume C is positive. There it is. Wow, it looks so super complicated. Can I simplify it in any way? Let me see. Full simplify. No, not really. So this would be the justification for still having the complex exponentials. The thing that making it look complicated is this combination of cosine and sine. And yeah, all right. I think to make a sense of this, I mean, okay, so I have obtained the solution much more quickly than I could do otherwise. And if you want to kind of get a sense of what the solution looks like, you can plot it. So let me just put this into solution. Let me just type it in. Solve equation 5 Q, right? So okay, let me put this into solution, and what I can do is substitute values like, okay, my L is equal to 1. I'm doing this in arbitrary units. And let's say Q naught is equal to 1. C is equal to 1. Let me put in a small value for R. R is equal to 0.01. I think that might be enough. Let me see. Yeah, so this is a function now I can plot. So I can take this, plot it as a function of time, and get something. And this is a kind of a way you can use. That looks weird. Let me have the time go from 0 to some relatively large value. Plot it from time from 0 to 100. There it is. Okay, 100 is not large enough. I need to say, let me make the R smaller or R bigger so that it'll damp out more quickly. Yeah, there it is. So it looks like a harmonic. It looks like a oscillation that's been damped over time. And so this is one of the techniques for working the computer algebra system. And sometimes complicated expressions that you get, it is easier to develop a sense of it if you plot it with some numbers. So, okay, let me stop it here. I think that's enough of a demonstration of using SageMath in context like dealing with time-varying circuits. But as usual, 20 minutes is a really small amount of time. Even for me, it's a really tight amount of time. So once I start, I will take care to kind of go through it quickly. Note the time. I have a clock here to help me pace myself. So I'll start. We have 20 minutes once I start. So start. Okay, so electromagnetic induction is Faraday's law, conservative law for situations. Yeah, this is a question where it's a lot of word description, so I'll do that. If there's a figure necessary, I'll draw that here. Answer descriptive, explaining if Faraday's law, model answer should describe in words, Okay, and okay, magnetic braking, when a conductor it slows down, for example. I have videos of that I help you, so if spinning, comes to stop. Yeah. So the key concepts and terms introduced in this context is really eddy current. Changing magnetic fields around the conductor causes eddy currents, which does a few things. Opposes any moving object responsible for the change in magnetic field, and dissipates away energy, Joule heating, with this energy coming from the mechanical energy. So that's the key thing, and I'll further explain the second paragraph. As the magnet moves, the magnetic field in a given region is changing, and the changing magnetic field plus the magnetic flux induces voltages according to the Faraday's law. If these induced voltages occur in the region with region occupied by a conductor, current loops form, which are called eddy currents. These currents dissipate away energy and break the motion of the magnet. Yeah, that feels detailed enough. You can also go into how the magnetic field produced by the induced current is in a direction that would oppose the motion of the magnet. But what I've written here is sufficiently detailed. An ideal electric motor has very little resistance to the voltage source, does not draw after a large amount of current. Explain how it happens. Start with the description of simple motor. Oh, diagram is okay. See diagram and attach the work. So what the diagram would look like is something like this. So we can imagine having set up a magnetic field. Let's set it up this way. I have North Pole here and South Pole here. That's my permanent magnet, and in between those permanent magnets I have a loop. So let me imagine having a loop like this, and around this loop, let's say I have current going in this way, flowing this way, and so on. So it doesn't matter. Yeah. So this is going to rotate, and it's sure that it's the work illustrating the current loop in a region of magnetic field. Actually, I'm not. Let me figure out the directions to make sure I've shown the rotation in the correct direction. So with this magnetic field, V cross the IL cross B. Yeah, so I think I drew the force on this segment of wire is actually downward. I cross B, yeah. The force on the, or from your perspective, it would be I is going into the page, so going into the page, and then cross B to the right. So the thumb is pointing downward. That's the direction of the force, and kind of the opposite on the other side. So this would be made to rotate counterclockwise. So in the magnetic field, rotating due to magnetic force on the segment of the current loop. In the absence of Faraday's law, this torque Faraday's law or motion induced voltage. This torque would mean that the loop is getting constantly angularly accelerated, and it wouldn't have a theoretical maximum angular velocity. Faraday's law means that voltage is induced in the loop due to the rotation of the loop, causing the magnetic flux through the loop to change. This induced voltage opposes the applied voltage, say Lenz's law. So at a certain angular frequency omega, the induced voltage completely opposes the applied voltage, and there is a zero net voltage around the loop, and no current flows through the wire of the motor. This demonstrates a mechanism induced voltage, i.e. Faraday's law, which limits the amount of current flow and the rotational speed of a motor. Yeah, that's the answer. 11 minutes. All right. Making good time, but I do have to kind of go quickly enough. In a circuit containing an inductor, the current through inductor does not change suddenly. Instead, a circuit containing a explains, describe how this happens. Okay, so it's asking for a circuit diagram. All right, let's just draw a circuit diagram. So you can imagine a setup like this, where you have a resistor. Because everything has a resistor, and not having resistor will make your model somewhat impractical. And you have an inductor that's all connected. And let's say you just found yourself in some situation where some amount of current I naught was flowing. Then this is what you want to think through. This current is flowing. It's flowing through here, which means there will be an induced voltage delta V here that comes from current times resistance. Now, this induced voltage, because of the way it's connected, it's the same induced voltage across the inductor here. And with the inductor, what you have is that induced voltage is equal to inductance times the rate of change of current, which means you now have non-zero rate of change of current, delta V divided by inductance. So this will cause the current through the inductor to change as a function of time, which will change how this voltage drop across the resistor is, which changes this rate, and so on. So to explain it, inductor and resistor starting with the current, so as the current I naught flows through the resistor R, there is a voltage drop according to the Ohm's law. This voltage drop happens to be the same voltage drop across the inductor, and from the inductor voltage relationship, delta V, for inductor, delta V is equal to inductance times di dt. This voltage across inductor means the current through the inductor will change at the rate di dt is equal to delta V divided by L. This change of current causes the voltage drop across the inductor, delta V to change, and so on. The current through the inductor changes at some rate until we reach I of t is equal to 0. I think that kind of explains it. There's a step-by-step explanation, and I haven't written down any differential equation other than this kind of basic definitional thing. All right, let's keep going. Do I have 5 minutes? Oh, 8 minutes. Okay, enough time. Okay, yeah, the negative sign in Faraday's law has a special name, Lenz's law. One person can say it's ensuring the conservation of energy. Oh, yeah. So using a concrete, detailed example demonstrate how Lenz's law does this. Yeah. So the example that I like the best, because it's a classic example, is this one. So imagine you have a region of magnetic field. Let's have them just coming out of the board, out of the screen. And within this magnetic field, we have placed a rail, a conducting rail. And across this conducting rail, we've placed a conducting bar. And the way I'd like to set up this situation is where this bar has some initial velocity v naught towards the right. Okay. So let me first work through the consequence of Faraday's law with the correct Lenz's law. So this bar moving to the right would mean electric flux through this loop is increasing coming out of the screen. That means induced current has to be opposing the change. It causes the current into the screen. So with the current into the screen, then the current direction that will be consistent with that is one flowing clockwise. So we should have current flowing clockwise. Let me just verify from my perspective. So wait. Flux is change in flux is coming out of the page. So I want to oppose it. I want magnetic field going into the page, and that means yeah. Okay, good. So with this current as it's being induced, this is what you have. You have current flowing down this rod this way, which means I can work out the magnetic force on this bar. I have current flowing down, and then magnetic field pointing out of the screen. Then the force is towards the left. There should be a magnetic force on this that's pointed to the left that comes from IL cross B. And this is actually all perfectly consistent with our intuition. You set something to start moving, and there are dissipative forces like this, which will cause it to slow down until it comes to a stop. I don't think I have any objection to that. So now let's imagine the version with anti-Lenz's law. So the anti-Lenz's law version would mean, well, let's figure this out. So anti-Lenz's law, it basically changes the direction of current. Let me make sure I have enough time. So this current, instead of flowing in the clockwise direction that we figured out, it would actually flow in the counterclockwise direction. That's the immediate consequence of anti-Lenz's law. Okay, as this flows, so that means my current is flowing up the rod. As I have current flowing up the rod, that means, to I cross B, your magnetic force is to the right. So instead of saying this, we would be saying our magnetic force is to the right. And I hope as you look at that, you see the absurdity of that. What it's saying is, you set up a rail in a magnetic field, you have something conducting here, you give it a little gentle push. If any of this could possibly be right, what it would mean is that thing that was gently pushed, it accelerates forward, it speeds up, because this magnetic force would be in the same direction as velocity, and it would just launch out. And that's absurd, because energy is conserved. If there isn't something that continues to provide more energy, like electrical energy, then when you push it a little, it should maybe move a little and then come to a stop. And that's what this picture describes. This is perfectly consistent with that. So, so when you consider the classic example of conducting rod sliding across a U-rail placed in a region of magnetic field, the direction of current you get with the Lenz's law results in direction of a force that is consistent with our ideas regarding the conservation of energy. That is moving things slow down with the loss of mechanical energy via sources you can identify. However, if we assume the opposite direction of current, then our analysis would conclude that the direction of force on the conducting rod causes it to speed up, patently in conflict with the ideas of conservation of energy, because such a result would create new mechanical energy. Well, new energy, period. Okay, did I have enough time? Yeah, that's probably enough time. So yeah, this is mostly word-based, although it does have place where I can attach this. So let me submit first, so that I won't get kicked out. Submit and I can copy and paste these figures, starting with the B. I had the B, so B. And then, okay, I think I can get C and D together. C and D. Okay, so yeah, that's this I pretty sure I got this from my final exams, past the final exams, and one of the things is it's a kind of, I think sometimes people fall into this trap of memorizing a bunch of formulas and trying to study that way, and the main purpose of this question was to try to get people to think conceptually, not over rely on formulas without understanding what they mean. So that's why this question is, it really prefers it's up here, inwards, and Faraday's law. Did I say? I think I mentioned the Faraday's law in every place. Yeah, is the current voltage. I guess here I didn't explicitly mention Faraday's law. It's fine. So let me do this freeform timed assessment demo. As I was saying, I didn't preload the dice this time, so there's a small chance that I'll get the same question, the one question I've done before. If I do, then I'll just reset it and try it again. So here's hoping that the first attempt will get the different question from what I've done before. And we got lucky. So let's do this. Okay, it says in this circuit shown below, they all have resistance R, voltage, capacity. Okay. Initially the capacitor is uncharged. Give your answer in terms of the given quantities. Let I be denoted. Let me start labeling this. This is hard to read and try to keep this stuff in my head. All right. So let's throw stuff so that I don't forget. I have current through the battery, IB. Write down the equation or equations you need to solve for IB as a function of time. You have to use a Kirchhoff's rule. And the reason I look dismayed is, you know what, I can actually make this a little bit simpler. I can treat this entire thing as one junction. Because even though they are drawn separated, they're not actually separated. That's junction 1. And I can treat this entire thing as junction 2. Then this is not quite as complicated of a equation. Because it's a circuit with only 2 junctions. And let's just start writing stuff down. So I got these branches. Let me label this IC, this as IL, and this as IR. Okay, this is making me think. I got 4 unknowns. So let's first write down the first equation. So equation 1, let's use junction 1. The incoming current, IB, is equal to the sum of all 3 outgoing currents, IC plus IL plus IR. And this junction number 2, if you're tempted to use it, don't use it. It'll basically give you the same equation, so I have to skip it. So I got 4 unknowns. one equation. I need 3 more equations. So those are going to come from my 3 loops. Let me write my loop equations this way. I'm just going to keep things simple. I'm just going to keep reusing this branch over and over. And each of my loops will go like this, and then go like this, and then go like this. Oh, let me, yeah, I think, so let me just, so this is the first loop that I would go. So let me do that. Or let me actually number my equations slightly differently. So I'll number this, my equation, as equation C for capacitor. So for that, my loop rule says I'm starting from here. Voltage rise, V naught, is equal to voltage drop across capacitor, which is going to be, oops, sorry, not equals. Voltage drop across capacitor, let me just put it this way, minus Q over C. I think that's the voltage change across capacitor. Yeah. And this sign kind of, it's associated with the relative sign convention for Q and IC. I think this will make, in a normal situation, Q positive minus ICR is equal to 0. And if I'm mistaken, all I get is a sign error that I can flip. So now let me do this loop. Again, the battery. This time the inductor and the resistor, and then around again. So L for inductor is going to be V naught. And then let me just do it minus L di dt. And I'm thinking, okay, initially the current will be probably increasing, so di dt will be positive. There's a voltage drop. I think that's right. If there's a sign error later, just invert the signs, this DIL. We'll deal with the sign errors later. And the equation R is now same thing. So, starting from here, loop, this time go through the resistor and then back. Minus I R. R is equal to 0. So those are my 4 equations for 4 unknowns. Yeah, so I'll say we get the following 4 equations in terms of 4 unknowns. We eliminate IC, IL, IR to solve for IB. And I'll write down the equations. IB is equal to IC plus IL plus IR. V naught is equal V naught minus Q over C minus IC times R is equal to 0. V naught minus L di L dt minus IL R is equal to 0. V naught minus IR R is equal to 0. So, good. At time t equals 0, what is IB? So I'm gonna use the hint, and by which I mean let's just erase some of these. It's possible that we don't need any of them. So if I need any of them again, I'll actually, sorry, that was a bad thing to do. Let me copy and paste this again, because I need to paste in my work at the end. So I don't wanna get rid of what I already do have for A. So let me actually write A here. This is work for my A. And let's do my work for B. That's gonna be. So we do the simplifications at t equals 0. So which is, no current flowing anywhere, which means I can eliminate this branch. The inductor is gonna make sure that no current continues to flow through this branch immediately after switch is closed. So inductor branch gone. It's open circuit. Now capacitor is gone, but in a different way. It's gonna go like a closed circuit. 0 charge across, 0 voltage, so it looks like just a wire. So I got basically 2 resistors in parallel. I guess my IB at t equals 0 is simply the voltage V naught divided by the equivalent voltage, which should be half of the R from adding the 2 identical resistors in parallel. So it should be 2 times V naught divided by R. Yeah. A very long time after, that is at a time which greater than all those time constants or the oscillation frequency. What is IB? So it's a different kind of thing. Let's redraw the circuit again. So after a very long time, again, the inductors and capacitor go away, but they go away differently for different reasons. Capacitor is now going to be fully charged, and there's a steady state, which means no current through the capacitor. dq dt is 0. So this entire branch is gone. It acts like an open circuit. And inductor is gone, but in a different way. Since a steady current is flowing, there's no change of di dt, so the voltage across the inductor is 0. There's probably some stored energy, but in terms of voltage, no voltage change. So you can treat this like just a piece of wire. So now you have two resistors this way. So our current somehow returns to the same value we are at. So at IB, t goes to infinity is basically the same thing that was there before. I don't know if I would have guessed that without working through this. But yeah, that's the answer you get when the resistances are the same. So how much time do I have? I got 11 minutes. That might be enough time to do but it says without solving the equations in part A. All right, sketch a rough quantitative. That's interesting. Yeah, so I think having done B and C gives me some idea. Because having done B and C, I know some asymptotic behavior of my current. So as a function of time, my IB, I know there will be some value that it's starting at, which is, 2V0 over R. It'll start at that value, and using this reference line, well, it'll probably come back to that reference line asymptotically over a long time. So the first thing I need to decide is, well, over time at t equals 0, is it gonna go up or down? I don't know. So I'm looking to see, let's paste in that thing again. Oops, not that. Paste in this thing again so that I have something to help me think through. So is there gonna be more current or less current? So this branch remains the same. This branch basically provides a constant value of half of the asymptotic value. So between these two, current through the C branch is decreasing, current through the L branch is increasing. Which is gonna be bigger, increase or the decrease? I'm inclined to say, well, let's see, voltage. So here the di dt is equal to, the entire voltage will be just across the L because no voltage drop here along the resistors. So di over dt will be V0 over L. And here, so I is equal to dq dt, and so double di dt is the double time derivative of that, and will that be q is cv, I think. Am I remembering it right? I think Q is a CV. I'm remembering that right. Capacitance times the voltage. So well, the voltage is not V0. At time equals 0, V is 0. So this double derivative, it's going to be C double derivative of V over dt. And the voltage across that's V0 minus I R. Oh, I see. So there was some so working it out, then di dt is C times double derivative of that. It's gonna be C times, this is constant, so minus R times the double derivative over T. Unclear. But I think, okay, so I think this is what I have. di dt here at time equals 0 is some constant value. And di dt through this branch, it's not a constant value. It depends on like a double derivative of current. And if I had to take a bet, this is lesser than this in magnitude. So if I had to bet, I would bet current would go up initially. And then I know it has to come back to this asymptotic value. So I think depending on component values, you could have some sort of like oscillation and then settle on here. Like that's a possibility. That's a possibility I'm willing to consider. Or it could be where it increases for a bit and then comes down. And so I think there are all those different choices. So what I would be willing to put on the answer is I would say, so we know the value of current starts at 2V naught over R and asymptotically ends at 2V naught over R. So my graph of IB would contain those features. In between, I'm not 100% sure what would happen without actually solving the differential equations above, but I would hazard a guess that the under reasonable conditions, because it's saying this, the current would rise first and then decrease asymptotically to the 2V naught over R value. I also think there may be a small possibility that this would undergo an LRC circuit ringing, which you will see in next week's lab. But attach the figure in the added work is for the possibility above. So I'll answer on this basis, and during the 20 minutes you are really not expected to do more than this. And I think I remember programming in a solution that included the SageMath code. So after submitting, we'll go look at my programmed in solution to see if I did that. But within 20 minutes, I think this is what's reasonably doable. And this is what I've done within 20 minutes or 16 minutes. So let me just submit this, and then I guess I have time to add work. So let's add work, and we'll go in and look at the programmed in solution and see if I coded in a SageMath code. If I did, then great. We can look at the SageMath code to see what the exact answer looks like. If I didn't, then we can curse my laziness and move on. I don't have enough time right now to, even without the time limit, I don't have enough time to do that coding right now. So let me, that's all the work, submit and end. So that's what I've submitted, save work, continue. And within this screen, I don't have access to the answer key right now, but I can bring in the instructor view and use that the way I also did for the multiple choice timed assessment, where I made the same mistake that ChatGPT made and couldn't correct myself well. Freeform circuit, so let me get that. Yeah, test student is the only student who's done it because I just posted this yesterday. So okay, so this is what's submitted, and this I don't have to display again, I'm pretty sure. Let's look at this answer. This is an open-ended question, yeah. Oh, I thought it decreases. Really? Not increase? On one version under, I guess it depends on the assumption. Yeah, so my answer was incomplete. With that, I guess, all right, sure. I'll try with the help of SageMath, a couple different parameters. So evaluate. So this is one, yeah. This is one where it decreases first and then increases. And I guess I must have programmed in this parameter. And I don't know if I expect the students to get this far. That's in 20 minutes. That's really a lot of. Like I didn't repeat that bit right now under time constraint. Opposite case where then and then is it not possible to get a ringing answer? I mean. So in order to get a ringing answer, you do need a small r, I think. Let's see, is it possible to get a ringing answer? So let me take this and just make r really small. Can I do that? Yeah, so I could make r. As I make r smaller, is that gonna mess up? Oh no, as I make r smaller, I think I'm gonna mess up this. So as I make the r smaller, yeah, maybe. It's possible that I don't get any ringing answer. So I'll try a few. So r at 10% of the original value. Does that. R at, I don't know, 1% of the original value. Yeah, it's possible that you never get ringing answer. Huh. I guess R being in every branch must introduce enough damping that you never get it. Okay, so I was actually, so one thing I am mistaken about it is somehow hoping to get this ringing answer. Let me just do one last try. What if R is really big? Like R 10 times what it was, and R 100 times what it was. And yeah, I think including R basically on every branch damps takes out energy quickly enough that it'll never actually ring. So okay, so I was mistaken about this possibility. And this is an open-ended question. Basically, any kind of thinking that I think this is an open-ended question. Open-ended, many answers are possible. I might need to say, as long as they get the asymptotic behavior correct, that should be considered fully correct. Yeah, so I'll do that edit actually, so that people don't have unrealistic expectation. Like all these details are some people what people are expected to get in the 20-minute time limit. I do think that's unrealistic. So right, that's it. That's all the time we have. So okay, so I'm gonna start the timer. So once I start, I'll have 20 minutes. And again, because I've never done these reviews before, whatever question I get, I'll just do it. Let's hope I get an easy one. I'm very tired. Get start. Okay, okay, it's gonna be a time-dependent circuit. Consider an LR circuit shown below. Like this, okay. Give your answer below in terms of given quantities, okay. Assuming that at time t is equal to 0, current through the circuit is 0. Find the current as a function of time. Okay, so what we have is, let me just sketch this out. So I'm just gonna say at t equals 0, I started applying voltage. So it's basically as though I connected a battery of a voltage V0. And I have an inductor, L, resistor R. And what it's telling me is the current as a function of time. And at t is equal to 0, current is 0. Okay, this is a boundary condition that will probably come into play. Okay, so it wants me to find the current as a function of time. Okay, so approaching time-dependent circuit, you use Kirchhoff's rule. You use this is a circuit with a one loop, so use Kirchhoff's loop rule to write down one of your equations of motion. So I'm gonna start from here, and then I go across the battery. I gain a voltage of plus V naught. Okay, let's keep going. As I go here, as I go across the resistor in the same direction as current, I lose voltage equal to minus I times R. And as I go across inductor, so this is where I have to think through, okay, what is it gonna do? So starting from here, I can only imagine current increasing. So with the inductor, what it's gonna do is the delta V is equal to L times di dt. So it'll either be plus or minus L times di dt. And I want to choose the sign that's consistent with all the other sign conventions that's been chosen or implied so far. So as I go across here, I think my di dt will be positive, but I want there to be a voltage drop here. It doesn't really make any sense for voltage to rise here. That would mean voltage drop across resistors greater than V naught. That just doesn't make sense. So I want voltage to drop here, which means this should be a minus sign. So let me make this minus sign. All these contributions to the voltage change as you go around the loop, they add up to 0. That's Kirchhoff's loop rule. And that will give you a way to write down your equations of motion. And once I have written one down, I look at it and say, okay, do I have enough, is one equation enough for the unknown quantities I have? So V naught that's known, R that's known, L that's known. So I as a function of time is the only thing that I don't know. So I think this one equation is enough. So from here, now what I'm going to do to try to solve this is, I'm going to use separation of variable. I'm going to say, okay, I and di, I'm going to try to put them on one side. I'm going to try to put dt on the other side. So I guess there's a few different ways you can go. The first thing I would do is I would put everything that doesn't depend on I on the other side. That would be V naught. So let me actually do it this way. I'm going to leave V naught on the left-hand side, and I'll move everything else to the right. That'll make it so that my things are positive. So I have IR plus L di dt is equal to V naught. Okay. I didn't do this right. Let me go back. So the very first step in using separation of variables is actually to solve for di dt. So let me solve for di dt. I'll just do that in my head to save a little bit of time. So doing that, having done that in my head, it's a V naught minus IR divided by L. That's di dt. So I want to now separate variables. I want to separate di and dt. The easiest way to do that, multiply both sides by dt. This is a slight abuse of notation in that dt is not a number. Like multiplying like this, that might not be right. I don't know in this particular context it gives me the right answer, so I'm just going to move on. So di is equal to V naught minus IR over L dt. And I think we don't have our variables separated yet. So right now, if I try to do an integral here, I would run into a little bit of problem in that this is not as a function of t, it's a function of I. So I want I to be on the left-hand side so that I'll have some functions of I on the left-hand side only. That's what separation of variable means. Each kind of side is a function of only one thing. So I guess the way to do that would be to take this, and I think I have to multiply by 1 over V naught minus IR. I have to kind of take the whole thing together to get rid of I on the right-hand side. So doing that gets me to di divided by v naught minus ir is equal to dt over L. Okay, I think that's enough to now integrate. I'm going to say I'm going to integrate this from t is equal to 0 to some final t, and that will be on the left hand side, that will be I going from my I initial value, which actually was 0 based on the description, and to some I final value, which would be I as a function of time, t final. So I think right hand side is easy enough to do. It's all constant. So doing this definite integral will get me 1 over L times t final. And the left hand side takes a little more work. I think I should do a u substitution. So let me say my u is v naught minus ir. That means du is minus di. So using these, I can kind of substitute. Substituting, I get. So when you do u substitution, so let me first substitute in the integrands. So di becomes minus du, and the denominator becomes just u. That was the whole point of this u substitution. And one of the things to remember to do when you are doing u substitution is to change the limits. You have to plug this into this expression to get what your new u's will be. So your u is going from v naught to an I-t, so it'll go from v naught to v naught minus I r. So, okay, I think I can do this integral. This is minus the 1 over u, the integral of that is natural log of u, evaluated limits from u is equal to v naught to v naught minus I is a function of time r. And plugging those in and evaluating, I get natural log of, so it's natural log of upper bound minus the natural log of the lower bound. Doing the natural log logarithm algebra, I get v naught minus I r divided by v naught. I'm just skipping that step so that save a little time. So okay, let me put this all together. So I have oh wait, sorry, I forgot a term. du was minus di times r. So here for di, I should be substituting minus du over r. So here it was minus 1 over r, minus 1 over r. Yeah, I forgot that. So let me put this together. I have left hand side minus 1 over r natural log of the thing is equal to the right hand side 1 over L t final. So I can solve for the natural log by multiplying through by minus r. So minus r here. So to get rid of natural log, I can exponentiate everything, exponent of e. Then what I have is on the left hand side, I get what's inside the natural log. v naught minus I of t final r over v naught. On the right hand side, I get all of that raised to e, or power of e to the minus r over L times t final. Okay, and I think I can solve for this current here. In the interest of time, I'm gonna do that in my head because I'm running out of time. So when you finish the algebra, I is a function of time. That should be equal to v naught. It's been factored out. 1 minus e to the minus, and I prefer to write it this way, t final divided by L over r. So that's your expression for current, which you could have looked it up from textbook. But wait, did I forget something? I forgot to divide by r from this r here. Yeah. So I of t is v naught divided by r times 1 minus exponential of minus t divided by L over R. Good. That's answer to 1. Answer to 2. Differential. Oh, I think I was trying to. So I figured people might just copy that from textbook. So going backward. It's r minus L times di dt is equal to 0. Yeah, and that's it. And in the work, I actually solved it. I didn't look it up from textbook. Typical value of resistance, what should be the on time P, so that at the end of the on cycle, the amount of current is, okay. So, I can do it this way. So I'm gonna use this as my main tool here. So for part B, what I would say is, okay, so I'm saying current after the time half, so P over 2, I want that to be I want that to be 75%. 0.75 of the max current, it'll be V naught over R. So I say, okay, so that is equal to the general expression for current, V naught over R times 1 minus e to the minus P over 2 divided by L over R. Okay, some things can simplify immediately. So I'm basically saying 0.75 is equal to that. And I think that actually allows me to say what E is. E to the minus P over 2 over L over R is equal to 1 minus 0.75 or 1 over 4, 0.25. So I can take a natural log of that to get minus P over 2 over L over R is equal to natural log of 1 over 4. Can get rid of that minus sign by flipping this upside down, natural log of 4, logarithm algebra, and I can solve for P over 2. Solving for P over 2, I have P over 2 is L over R times natural log of 4. Good. P over 2 should be equal to L over R times natural log of 4. Oh, so since they give us the numbers, 1,000 ohm, 10 to the minus 2 Henry. So 10 to the minus 2 divided by 10 to the 3, so it's 10 to the minus 5 times natural log of 4 seconds. Okay, so it's on the order of like a fraction of a millisecond, a little larger than microsecond. Guess that might be right. Okay, let's keep going. Assuming that to describe what's the maximum energy stored in the circuit. So with 0.75 or with a 75% of current, or rather at 75% of V naught over R as current through the circuit, the energy stored in the inductor, the UL, is equal to 1/2, I want to say Li squared. I hope I have a correct formula memorized. Is equal to U of L is equal to 1/2 times L times, and the current 0.75 V naught over R squared. Think given quantities of, so because they gave us the or let me do the next part, and if there's time, I'll plug in numbers. So extra AC circuit question is that you derive with that. Find the expression for amplitude current to those given quantities. Current through the circuit is find an expression for I. So what it says that I naught is equal to V naught divided by G equivalent. And G equivalent is the impedance of the resistor R plus impedance of the inductor I times omega times L. So I naught is equal to V naught divided by, and I have to say it's the absolute value of the G equivalent. And since absolute value of G equivalent is equal to square root of G equivalent to complex conjugate times G equivalent, which will be square root of, I'm gonna do this in my head, R squared plus omega squared times L squared. I naught is equal to V naught divided by square root of R squared plus omega squared times L squared. And that it makes sense at higher frequencies your current will be less with the inductor opposing it. Okay, so let's plug in the numbers. I think we have time. So this is what we are plugging numbers to. So let me actually minimize this briefly so that I can have all from alpha on the side. So we had the values. The inductance was a millihenry, and the voltage was, were we given voltage? We were not given voltage. Oh, that's a bummer. So let's say voltage is 10 volts. And the resistance would be 1 kilo ohm. And the main thing I want to check is I want to make sure my units come out right. Because if my units come out right, that would mean I remember the formula correctly. If they don't, that means I didn't remember correctly. Okay, units come out right. So if the applied voltage V naught is 10 volts, this gives us maximum stored energy of 0.2813 microjoules. Good. Okay, so that's I think everything. We got 1 minute remaining. I put in everything. It's not auto grading, so it doesn't matter. I think 1 minute will be enough time for me to add work. So let me add work. So I need my OneNote. I think I can just do something like this. Let me dock it the way it's meant to be. Okay, so I 8. This is where I started. I don't think I'll have actually time to finish it entering work. Yeah, let me submit an end, and then I'll add work. So submit an end, and then add work. All right. So this is the whole thing for the part A, which took a while because that's a sort of the design of this multi-part question where first part takes a long time. So it's not necessarily meant to be done in an equal amount of time per part, which makes some of the pacing considerations tricky because you spend more than 5 minutes on part A and I start to panic, like to have enough time to finish off all the remaining questions. Okay. All right, that's A and B, and I think C and it just had the things written. Okay, yeah, so that should be it. If I didn't forget something, I haven't programmed in the solutions for these questions yet, but all this should be right. I don't think I made the mistakes. So yeah, this is the time-dependent circuit question, and it's perhaps the most calculus-heavy portion of this class because it's so far like when we apply Gauss's law, apply Ampere's law, we pretended to do integrals that we never did. Time-dependent circuit, we actually do the integrals, so it's the most calculus-heavy part of the course.